I left off last video with the assertion that I could not calculate what my mixing point was anymore because I don't know what E2 or R1 are. Therefore, there is no one equation, one unknown. However, what I can do is start with my stage 1 material balance and rearrange it to get it into terms of stuff that I know. So I could say that F minus E1, these are both numbers that I know, so I could say 100 minus 236 is equal to some number. This may seem strange, but stay with me for a minute. I'm just going to call it delta, right? So I know that the actual value is minus 136 just by doing it in my head, but I'm going to keep it general in terms of variables for now. All right, and then by rearranging that equation, I would say that F minus E1 also must equal R1 minus E2, right? Simply by starting up here with what I knew from before, take E1 over to the other side, take E2 over to that side. And then look at what happens. So if I do a stage 2 balance, so I'm going to sketch it in up here, stage 2, where I've got R1 coming in, R2 coming out the other side, E3 coming into stage 2 from stage 3, and E2 coming off of stage 2. I can do a similar material balance here where I say R1 plus E3 is equal to E2 plus R2. And then again, I don't know any of these four variables. However, I do know what R1 minus E2 is. So if I take E2 over to the other side, take E3 over to this side, I end up with the equation R1 minus E2 is equal to R2 minus E3. And then I already know that R1 minus E2 is equal to delta because this was what my stage 1 material balance told me. So similarly, I can say that I could just make a chain here. R2 minus E3 is also equal to the same number. And you can do this for yourself. So go on to a hypothetical stage 3. So keep doing this, dot, dot, dot. And I'll say that these are all equal to delta. And a couple lectures ago, remember I told you that it's helpful to think of F as not F, but as R naught, and to think as S is E of stage n plus 1, such that I can generalize and say that R of stage n minus E of stage n plus 1 is equal to delta. So what is this delta? It's conceptually, I think, difficult to understand, but I'm going to try and make an analogy that it's similar to the mixing point. However, it's not really the mixing point. So the mixing point, when I had cross current, related the incoming stream. So it related what comes in to what goes out. But now, because I don't know both incoming streams, I only know the crossing streams, I'm saying that every pair of crossing streams in this extraction has the same difference in flow rate. You can prove that with material balance. It's equal to delta. So on the other side, I started with F minus E1 is equal to delta. On the last stage, you could say that Rn plus S is also equal to delta. And similar to how we solve problems graphically by saying that if I can write an equation like F plus E2 is equal to M, then these 3 points must lie along the same line. I can do the same thing with delta. I can say that the 3 points Rn, E1, Rn, E of n plus 1, and delta all lie on the same line, all collinear. And this will allow me to find where the composition, I say composition in quotes, what is the composition of delta? So I'm going to pause the video to get my equilibrium diagram closed. So I've got the same diagram before, and although I could find the composition of delta by doing similar material balances, I'm going to make the point that I can just simply draw lines, and wherever they intersect must be the delta point because the delta point is common to all stages. So I've already labeled F E1, come on, I can't get my pen, E1 and F are on a line. All right, and now I can see that if I just draw the line and stop it there, then I'm saying that the delta point should be collinear with both F and E1 and R and S. Obviously, the way they look now, it kind of looks like they're parallel. So instead of stopping the line there, I'm going to extend the line further. So I'm going to go to F to E1 and then extend it all the way out here. Similarly, I've got Rn to S, and I'm going to extend that line out here as well. So this is going to give me what my delta point is. Now, obviously, it looks a little bit strange. We're not even in the same space as the plot anymore. It all has to do with this minus sign in the material balance. So that's why we're kind of outside the realm of what you would expect. Now, I know I mentioned that you can calculate what the composition of delta is with similar material balances. You can say that xi of Rn times Rn minus xi of En plus 1 times En plus 1 is equal to xi delta point times delta point. And you can get the flow rate of the delta point just by solving one of these material balances. I've just shown you that delta is 100 minus 236 minus 136. And now I could plug in any of the points that I've solved for so far. So I already know what F is, so I'll use R naught to figure out what the compositions of the delta point are. But what you should find, and what should be initially alarming, but then be okay, is that one of the flow rates would be negative. So if I look at like what the space of this plot is, remember that this line out here corresponds to water is equal to 0. So the coordinate that's out here is water is less than 0. So if I figure out what x water at the delta point is, you should find that it's less than 0. And while initially that would spark some alarm, because remember, your compositions has to be between 0 and 1, but for the purposes of the delta point, it's not like a physical thing, right? It's just a tool that we're using to solve material balances a little bit easier. Just graphically, I can look and say that X acetic acid of the delta point is approximately equal to 0. And then X of vinyl acetate for the mixing point has got to, I'm sorry, the delta point has got to be greater than 1, because vinyl acetate equals 100 is on this line and moving upwards as I go that way. All right, so knowing where the delta point is helps you, because it is going to be common to all points, all Rn's and En plus 1s. So I'm going to clean this up a little bit and kind of step you through the solution procedure before I show you nicely how to do it in the second half of the practice problem. So I'm going to, I already found where the delta point is. I'm going to say that E1 is connected to R1 with a tie line. So tie line across, R1 is here. And then I know that by following my formula here, R1 minus E2 is equal to delta. All right, so this means that R1, E2, and delta all lie along the same line. So if I draw a line that connects R1 to delta, I can figure out where E2 is supposed to be. So think for yourself for a second, where along this line could E2 possibly be? And the answer is, just like E2 comes off of stage 2, so anytime something's coming off of a stage, it must be in equilibrium with something else. Therefore, my E2 point must lie there. Now that I know E2, I could draw another tie line, and I know this is getting very small. I'll go through this in a little bit greater detail in the practice problem. E2 and R2 are connected with a tie line. Then R2 minus E3 is connected to delta with a line again. So I keep drawing lines from delta to R of stage N, and wherever that line that I draw that connects Rn to delta crosses the equilibrium curve on this side must be where the composition of E2 is. So I'm going to stop this video here and get into the practice problem, which is a continuation of last time's practice problem.